Hi everybody and welcome back. So now what we're going to do is we're going to look at our scenario here where we have three distinct points that lie on some plane. We don't need to draw out those points. It's okay. We don't need to make the axis, and specifically we don't need to draw it out because it would be a three-dimensional point, and the challenge then would be to draw a quite sophisticated three-dimensional diagram that would capture the essence of where those points are, and then some kind of drawing of a plane that would have an obscure angle on it that would be able to encapsulate those 3 points. Quite a challenge, and remember that's not required for us because all we need to do is establish an equation. So an equation of a plane will require a position vector that gets us up to the level of the plane, plus a direction vector. Okay, that's an S, plus another direction vector, and S and T would be elements of real numbers, and the two direction vectors will be able to establish the fact that they are distinct from one another, distinct directions, which will get us a spanning set, and the position vector will essentially get us to the level of the plane that we're talking about. Now, the position vector is extremely easy because for the position vector component of our plane equation, all we need is just 1 point that lies on the plane. So when it comes to the position vector, you could actually use any one of these 3 points as your position vector. So that's the easiest part of the whole thing. The harder part is establishing two different direction vectors that can be used to form a spanning set. So the way we would do that is we would just we would create vectors out of any two of the points, okay? And we do it twice because we need two different direction vectors. So even you can see that's not actually that challenging, is it? I hope you don't find it that challenging because we know how to create a direction vector between two vectors. So what I'll do is I'll just create vector A, B as one of our direction vectors, and AB will be the vector that starts at A and ends off at B. So it's got its tail at A and its head at B, and vector AB will simply be the head of the vector minus the tail. That will be the X component. The Y component will be the head of the vector, minus tail. That'll be the Y component. And the Z component will be the head of the vector. Okay, it's the vector that starts at A and ends at B, minus tail. And then we'll just simplify that, right? That equals to -1 plus 1, which is 0. And then 1 minus 3 is -2, and 0 minus 8 is -8. Okay? Now, here's an interesting thing. That vector there represents a direction vector that we can use on our plane, and or if you like, any scalar multiple of that vector, right? So here's an interesting fact. I could take vector AB, factor out a -2, and come up with 0, 1, 4 as an equivalent vector that has just been scaled down by a factor of -2. You see what I mean? And this is a nice simple vector. It is on the same vector direction as this vector. It's just I've scaled out, I've taken a scalar out of it, I've scaled it down by a factor of -2 and rewritten it with positive numbers. And that still has the same direction, it's just a scalar multiple of my original. So I don't have to do that, by the way, okay? But I'm going to do that because I like those numbers a little better. They're kind of cleaner numbers, right? So that's the direction of vector AB. Now just pick another one. How about we do BC? Let's do BC as our second direction vector, okay? So we'll do that over here. So vector BC will be the vector that starts at B and ends at C, and that's going to equal 4 minus -1, 1 minus 1, and 1 minus 0. Okay, 1 minus 0, and let's just get rid of that for a second here. So what does that give us? Well, that gives us the following. It gives us 5, 0, 1. Now, I don't think there's a nice scalar that will work with that. I mean, you could, once again, scale it up or down by any amount you want, but I think that, there's not something that's divisible. Those are some prime numbers there. 5 is a prime number. So we're just good with that. I mean, you could multiply it by 2 and have 10, 0, 2, but that won't really be any neater or nicer. Okay, but see, now we're really close to the end now, because now we have two direction vectors. We got a direction vector of 5, 0, 1, and we got a direction vector of 0, 1, 4. So our plane equation is going to be, now you're going to pick any one of the points that lie on your plane. I'll pick 1, negative 1, 3, 8. Okay, so the equation of the plane is going to be the position of the plane, which can be established by any point that lies on the plane, plus S 0, 1, 4. Okay. Oops, I don't want a parallelogram. That's 0, 1, 4 plus T. And then our second direction vector was 5, 0, 2, right? 5, 0, 1, sorry. Okay. 5, 0, 1. And then the communication piece, always a little bit, something people forget. S, E, R, T, comma, S are elements of real numbers. And that right there is the vector equation of the plane. Okay, the parametric equation just breaks it down by its x and y components. Very easy. So the x parametric equation of our plane, and if you want, you can, if you want to make sure that you're communicating to me, we can call it. We can put that little pi symbol in because it's the first plane we've been talking about. So pi 1, that would be equal to the x component of the position vector. Now 0s won't even be there because 0 times anything. Okay, so the x component of the plane as a parametric equation is x equals negative 1 plus 5t. Okay, the y component of the plane will equal 3 plus s, okay, and then 0t. And the z component of the plane well, that will equal 8 plus 4s plus t. All right, and once again, s and t are elements of real numbers. And these are the three parametric equations that represent the equations of the pre-parametric equations that represent the plane. And obviously those are not unique on the plane. They just represent a sampling of what you could say about this plane, because remember that I could have chosen a different position value from my 3 points, but it's okay, because what we're saying here is simply that these are 3 parametric equations that are consistent with being on the plane. And there's all kinds of points that would be consistent with being on the plane. We're just trying to establish some basic kind of parameters for this plane that would agree with the characteristics of it. And these 3 equations agree with the characteristics of the plane, but they are by no means the only 3 parametric equations that could be used to describe this plane, and neither are in the vector equations. In the vector equation above, obviously it could look quite a bit different depending on how you choose your spanning set. But the one thing that would be true, and this is the visual part that might be hard to picture, is that regardless of what the vectors you chose for, they would have to be consistent with being on that particular plane. And so there could be a wide variety of vectors, but they would all exist on the plane that we're talking about. And so, yes, there is a visual aspect to it, but you basically just at this point have to trust the math. And, you know, sometimes I understand that can be challenging, but they will produce consistent results if we were to, for example, test points, which we'll do in a later video. The parameters for S and T will be consistent across your various parametric equations if the points are all on the same plane. We'll get to that in another video, so testing whether a point actually does lie on a plane. But for now, that's good. But that will be something that we look at further, is how do we know if a point lies on a plane? And it's very similar to how do we know that a point lies on a line. You plug in a point, and if it produces a consistent parameter for S and T, then you know you got a point that agrees with the plane. All right, thanks, and thank you for watching.